Good morning. So today we will discuss about electrophilic substitution reactions of aniline. And before we go to the electrophilic substitution reactions of aniline in detail, what is the effect of amino group in aromatic rings on the electrophilic substitution reaction? So we know that an amino group is a strong activating group. And also we have studied that an amino group is an ortho-para directing group. So here is an example of an electrophilic substitution reaction of aniline, which is bromination. So when I treat aniline with bromine in water, you can clearly see that the three positions, the two ortho positions and one para position, they are brominated. So this reaction undergoes very easily. This bromination the aniline undergoes bromination very easily. That is, the amino group is a strong activating group, and also amino group is an ortho para directing group. And why amino group is an ortho para directing group? Why amino group is a strong activity? That we are going to discuss in this class. So why amino group is a strong activating group? We know that in amino group there is a lone pair of electron, so which can be donated to the benzene ring. It's known as pi donation. So the electronic charge distribution or the electronic density, the negative charge density inside the benzene ring increases, which will facilitate the attack of an electrophile which is having a positive charge, or an electrophile is a negative charge, electron loving species. So it can easily attack this benzene ring because the charge density, electronic charge density inside this benzene ring is increased due to this pi donation. That is why amino group is a strong activating group. Now, why we say that amino group is an ortho-para directing group? We can explain this thing. I can justify this ortho-para directing effect by two things. One is by charge distribution. So when I draw the resonating structures of aniline, you see this lone pair, if it is donated, double bond comes here, so that this goes here. So when this lone pair goes, here comes a positive charge. So this double bond, so the negative charge comes here. You see, comes here, so the negative charge is here. Now, in the next resonating structure, this pair of electrons comes here, so the double bond becomes here. So this bond goes here, so the negative charge here. Now in the next resonating, it goes here, so the double bond comes here. So this bond shifted here. So you see the positions of the negative charge. In the first structure, resonating structure, you see the negative charge is in the ortho position. Now it's in para position, again in the ortho position. So no electronic charge density or accumulation at the meta position. So the electronic charge density is more, the negative charge concentration is more at the ortho para positions. So from this, it is clear that a negative charge loving electrophile will be more preferably comes to the ortho para positions. So using the concept of electronic charge distribution, we can explain why an NH2 group is ortho para directing. Similarly, I can explain this concept. I can explain the preference of ortho-para attack of an electrophile in aniline, or when an amine is present, when an amino group is present, also by stability of sigma complex. What do you mean by sigma complex? Sigma complex is the carbocation formed by the initial attack of the electrophile. So here, this is ortho attack. When electrophile is attacked on the ortho position, the positive charge is here. This is para attack. You see, when the electrophile is attacked, the para position, the positive charge is here. This is meta attack. And now you draw the resonating structure. So this bond comes here, the positive charge is here. Similarly, this comes here. The positive charge will be here. The double bond will be here. The positive charge will be here. And since this positive charge is here, so this can come here. So a double bond can be formed here using by the pi donation. So these are the resonating structures of the sigma complex when there is an ortho attack. Similarly, in the para attack, we can draw the resonating structures. So if this bond is shifted to here, okay. Now the same thing happens with this pi donation. Next, you see, when this goes here, this is shifted here, so double bond comes here. So this double bond will not be here, it goes back. You see, four resonating structures. Similarly, in the case of when there is a meta attack, you see the positive charge is here. So this bond the positive charge will be here. Okay. Now again, this bond is shifted here. So these are the resonating structures in the case of meta attack. So in the meta attack, there are only 3 resonating structures, while in the ortho and para there is an extra resonating structure due to the presence of positive charge just below on the carbon atom containing the amino group, just below the amino group, so that there is a possibility of an extra resonating structure which gives an extra stability for these two sigma complexes. For example, for the sigma complexes formed by the ortho attack and para attack. The sigma complexes formed by the ortho attack and the para attack are much more stabilized compared to the meta attack because of the presence of the cation, presence of the positive charge just below the amino group. Okay, so when the amino group is present, the electrophile will preferably comes to the ortho para position. In this way also we can justify the preference of the ortho para attack of an electrophile when there is an amino group is present. So basically aniline, when it undergoes electrophilic substitution reaction, normally the electrophile comes to the ortho or para position. Okay, thank you.